Which of Newton's laws states that an object at rest tends to stay at rest, and an object in motion tends to stay in motion with the same speed and in the same direction unless acted upon by an unbalanced force? Is it the first law, the second law, the third law, or the fourth law of Newton? The answer is: we experience forces every day and most of them are visible to us and easily demonstrated, such as pushing or pulling actions. Some forces are invisible to us also, such as electromagnetism. Forces are essential throughout the history of humankind in the development of its society through various technological developments. Here we will talk about the laws established by Isaac Newton. Isaac Newton came up with the 3 laws of motion. Now, these laws became a basis to determine the relation of acceleration, motion, and mass of the body. These laws are quite useful in determining the motion of systems. The first law of motion, also called the law of inertia, which can be stated that any body will remain at rest or in motion in a straight line with a constant velocity unless acted upon by an outside force. So a body like a particle remains at rest until it is changed by an external force. The second figure remains in motion unless it is stopped by a force or changes its direction. We note that for objects having greater mass, it would require a greater amount of force to overcome its inertia in order to accelerate it, but once it starts to move it gets lighter. Similarly, it would require a greater amount of force to stop an heavier object that is moving. The second law of motion is also called the law of force and acceleration, or sometimes called the law of momentum. It relates the proportionality of the force or net force is equal to the mass of the object times acceleration. In the figure we see that heavier objects would require more force in order to accelerate it. The third law is also called the law of action and reaction, which states that whenever a body exerts a force on a second body, the second body exerts a force back on the first that is equal in magnitude but opposite in direction. If we examine the swimmer in the figure, as he pushes the water backward, which we will call the action force, the water exerts an equal amount of force on the swimmer as the reaction force. So when you push an object exerting an action force, the object will exert the same amount of force to you as the reaction force. Let us look at the figure. If you ever have ridden a plane or car, you may have noticed this type of experience where you feel a sudden force as the vehicle moves from rest, then disappears once it is now moving. In this case, let us say you are on a plane and as the plane takes off you feel being pushed backwards into the seat. The question is, why do you feel being pushed back into the seat of an airplane on takeoff? Let us try to explain this in terms of Newton's laws. The first law or law of inertia states that a body at rest will remain at rest unless acted upon by an external force. For this case you are that body who is at rest and the plane would be the source of external force. The plane would exert a force onto you, changing your state from at rest to motion. This happens instantaneously until you and the plane will move at the same acceleration where you would feel more comfortable, which can be calculated using Newton's second law. The amount of force exerted by the plane will be pushed back by an equal but opposite in direction by the body. Comparing these 3 Newton's laws, we see that Newton's first law or law of inertia would fit this definition, that an object at rest tends to stay at rest, and an object in motion tends to stay in motion with the same speed and in the same direction unless acted upon by an unbalanced force. In a simple harmonic motion, the restoring force is directly proportional to the blank. Letter A, displacement from equilibrium, letter B, velocity of the object, letter C, time elapsed, or letter D, frequency of oscillation. The answer is in our daily life we experience things like the repeating motion of the ocean at the beach or devices to monitor time. The behavior of these things are what we call periodic motion or oscillation. It is simply defined as a repetitive motion that acts over and over. A body that undergoes a periodic motion has a stable equilibrium position, or in simple terms a position where it always goes back and typically the origin point. Let us examine some forces that cause oscillation. Here we have a block lying on a frictionless surface attached to a spring with a spring constant K. The block is allowed to oscillate back and forth. Here we have the physical quantities that we take note of. X here would be the horizontal displacement or the path that the block will travel when it is oscillating. N here would be the normal force due to the reaction of the surface with respect to the weight of the block. Of course, the weight is also due to the gravitational effects. Then we have the force X, which is the force exerted by the spring as a reaction of the spring during oscillation. We see that when it is at the equilibrium position, the force present is simply the normal force and the weight. There are no forces present in the horizontal or x-axis. When the spring is compressed to a distance x, the spring responds with an equal force that pushes the block in the opposite direction as shown in figure B. This is the natural response of the spring, which we will see also at the third scenario when the spring is pulled. The force here is going in the opposite direction as a response to being stretched. Let us look at some terms. The length x when the spring is expanded is called amplitude, and its is the maximum magnitude of displacement from its equilibrium. So, in a frictionless surface, this x will be moving back and forth from the equilibrium position. Cycle is the complete vibration or one complete round trip made by the block that undergoes periodic motion. Looking at the figure below, we have a pendulum moving from an initial position and final position is the same. So, one cycle of the pendulum is just one rotation of the block where it ends at the position where it started. Simple harmonic motion, or SHM, is the simplest kind of oscillation. Occurs when the restoring force F is directly proportional to the displacement from equilibrium x, as shown by the equation F equals to negative kx. As shown earlier, a block oscillates in a periodic motion, but the force that initiated this motion is an external force, which we must understand by now that its magnitude is equivalent to that of the restoring force exerted by the spring. Now, as we release this body, it will continue to vibrate in a simple harmonic motion. Objects that undergo simple harmonic motion are called oscillators. The tendency of an object to remain at rest or in uniform motion in a straight line is described by blank. Letter A, inertia; letter B, momentum; letter C, acceleration; or letter D, gravitational force. The answer is the tendency of an object to remain at rest or in uniform motion in a straight line is described by Newton's first law, which is also called the law of inertia. The other physical quantities are described as the following. Momentum is a fundamental concept that describes the quantity of motion an object has. One important aspect of momentum is that an object with a larger mass or a higher velocity will have a greater momentum. If two vehicles collide, we have to consider the difference of their mass and speed. For this case, where a truck collides with a car moving at the same speed, the truck will have greater momentum. This has nothing to do with the condition stated in the problem. Acceleration is the rate of change of velocity over time, which has nothing to do with the scenario being presented in the problem. Gravitational force is a physical quantity that is in relation to the gravitational effects. Objects having greater mass will have greater gravitational force, or for this case in the figure it will be the difference of weights. When an object moves in a straight line with constant speed, which of the following is true about its acceleration? Letter A, the acceleration is 0. Letter B, the acceleration is constant. Letter C, the acceleration changes over time. Letter D, the acceleration is inversely proportional to speed. Let us look at another physical quantity called acceleration. Acceleration is a vector quantity that describes the change in velocity over change in time. Its unit is described as a meter per second square. A symbol of letter A and a formula of V final minus V initial over T final minus T initial. Based on the equation, so if the object speeds up it would generate a positive acceleration and if it slows down it would be negative acceleration. So, if the object moves at constant velocity then its acceleration is zero. According to the law of conservation of energy, the total energy of an isolated system remains constant. Which of the following best describes this principle in classical mechanics? Letter A, kinetic energy is always conserved, but potential energy can change. Letter B, both kinetic and potential energy can change, but the total energy remains the same. Letter C, the sum of kinetic and potential energy is always zero. Letter D, energy is not conserved in classical mechanics. The answer is here we have a ball falling from a height h1. The ball falls from rest thus having zero initial velocity. At the second state, the ball will have both kinetic energy due to the motion of the ball, and potential energy due to its elevation from the ground. At the final state or at the ground, the ball will have a final velocity before coming to rest, and it has zero potential energy since the height is now zero. We see here that the potential and kinetic energy changes but the total mechanical energy, which is the sum of both kinetic and potential energies, will be the same at every state. Here we have a simulation on the changing kinetic and potential energy. We see that at an initial point when we place the skater on top of the track it has only potential energy. This potential energy is due to the gravitational effects and once we release the skater it begins to move. The energy is being converted to kinetic energy. When it moves to the opposite side, we see it slows down and eventually stops. As the speed slows down the kinetic energy reduces and the potential energy is increasing. So the energies simply transform from one form to another and at every point in the track, the total mechanical energy remains constant. When an object moves in a circular path at a constant speed, which of the following is responsible for keeping the object in motion? Letter A, inertia. Letter B, centripetal force. Letter C, gravitational force. And letter D, centrifugal force. The answer is here we have a carousel moving in a circle at constant speed. Looking at the forces that influence one of its horses as shown on the right. We see that there are three main forces that act on the horse. The tangential force, which is the force associated with the acceleration tangent with a circular path. The next one is the centrifugal force. This force is associated with the acceleration going outward of the path. The last one is the centripetal force. This force is associated with the acceleration going inward and keeps the object in motion in a circular path. Here we have a car moving on a curved road and it experiences several forces. If we focus on the perpendicular forces with respect to the curved path, we have the centripetal and centrifugal forces. The centrifugal force pulls the car outward and this is due to the inertia of the car. The centripetal force is the one resisting the centrifugal force by pulling the car towards the center and it is given by the force between the car tires and the road. This force that is present between the car tires and the road is the frictional force. This frictional force in this scenario keeps the vehicle in the curved track and in motion. In this scenario, we have the Earth with the Moon moving around it in a circular path. We consider the gravitational force that keeps the Moon in orbit and in this scenario this would be the centripetal force. If we turn off gravitational effects, the gravitational force would be zero and we see the Moon would be shot to outer space. This shows that the gravitational force which acts as the centripetal force to keep the Moon in circular motion. In a one-dimensional collision between two objects, what quantity remains conserved if no external forces act on the system during the collision? Letter A, linear momentum. Letter B, kinetic energy. Letter C, velocity. And letter D, angular momentum. The answer is here we have two spheres colliding in two different scenarios. The first one scenario is where they collide elastically. Here we see that the spheres separate after collision. In this case both their momentum and energy or kinetic energy are conserved. The second scenario is where they collide but they move with the same speed and move in the same direction. This collision is called the inelastic collision, and in this case their momentum is the only parameter conserved. So the answer to the question regarding the quantity that remains conserved, if no external forces act on the system during the collision, is conservation of linear momentum. A block is sliding down an incline. If the coefficient of kinetic friction between the block and the incline is known, which of the following equations can be used to calculate the acceleration of the block? Letter A, which is the acceleration is simply equal to the gravitational acceleration. Letter B, the acceleration equal to the function of sine and cosine theta. Letter C, the acceleration is a function of sine theta, and letter D, the acceleration is a function of cosine theta. The answer is: first we draw the problem based on the given parameters from the problem. So, we have a block of mass m lying on an inclined with an angle given as theta. There is also the friction that is related to motion of the block, so it is a kinetic type of friction. Since the object is subjected to gravity, then we have the weight of mass m, and since it is lying on the incline which pushes the block, then we also have the normal force. We then redraw the problem using the free body diagram method. Free body diagram allows us to simplify the problem by drawing the forces into an appropriate coordinate system. For this case it would be the Cartesian coordinate system. Here the forces are simply placed redrawn onto the x and y axis. Here we use the plane of the inclined as the x-axis for simplicity. As observed, the weight is lying neither on the x or y axis, so we split the weight into its components as shown as weight along x and weight along y. We then sum the forces along the components. For the forces along the x-axis we have equation A. We see that the force along x is equal to mass times acceleration. This suggests the motion of the mass going downward the plane. For the forces along the y-axis we have equation B. We see that it is equal to 0 since there is no motion along the y-axis. In the y-axis we can obtain an expression for the normal force. We then combine the expression obtained from the x and y axis. So, we have the normal force from equation B to equation A, and we have equation C. Rewriting it further to solve for the acceleration expression, we get equation D. According to Kepler's laws of planetary motion, what is the shape of the path that a planet follows around the Sun? Letter A, circle. Letter B, ellipse. Letter C, parabola. And letter D, hyperbola. The answer is: Johannes Kepler was a German astronomer, mathematician, astrologer, natural philosopher, and writer on music. He has contributed significantly in the scientific revolution and is best known for his planetary motion. The motion of planets is described accurately by Kepler laws of planetary motion. These empirical laws are mainly based on the data collected by Kepler mentor Tycho Brahe. The first law states that each planet moves in an elliptical orbit, with the Sun at one focus of the ellipse. Kepler's second law states that a line from the Sun to a given planet sweeps out equal areas in equal times. Here we see the areas can be divided into several parts but of equal areas at all times. Third law of Kepler states that, the periods of the planets are proportional to the powers of the major axis lengths of their orbits. Shown in the simulation, as the major axis denoted in a changes, the period t also changes. And it appears to have a directly proportional relationship. Comparing the three laws of Kepler, we can deduce that the first law describes first the shape of the orbit, which is elliptical in pattern. In planetary motion, it is always true that letter A, total angular momentum is constant in magnitude and direction. Letter B, angular speed remains constant. Letter C, linear speed remains constant. And letter D, neither the angular speed nor angular momentum is constant. The answer is looking at the velocity of the object, it appears to change as it moves in elliptical orbit. We see that speeds up when it is closer to the larger mass. It slows down when it is farther away as shown in the first law. So we can say that the velocity is not constant for planetary motion. Similarly, the angular speed also changes as it moves around the orbit. This can be seen in the figure in second law. It may sweep out equal areas at all times, but the speed changes when it is closer or farther away from the Sun. Considering the formulation of angular momentum as shown here, where m is the mass and it is constant. The r here is RTHE distance between the Sun and Earth. And v is the speed of the planet. When the distance between the Sun and Earth is small, the planet moves faster. Its angular momentum is given here. When the distance is large, the planet moves slower. So we see the inverse relation between the distance and speed. This results in a constant amount of angular momentum with its direction pointed perpendicular to the plane of the speed and distance. The end for now. For questions and comments you may send them to diyslearningstuff@gmail.com. You may review the slide on YouTube at Dies Learning Stuff. Thank you for watching and see you in part B.